So this is next unit for us, right? The unit name is current electricity. So till last lectures, we talked about electrostatics. Electrostatics basically means the charge which is at rest, right? The steady charges, right? So charge has no velocity, there is no motion. But when we will talk about current, this current word anywhere you hear, even it is water current, air current, any current, it means something which is in motion, right? So if charges are given motion, it constitute a current, right? It constitute a current. So let's say we said that if any electric field is applied, right? If any electric field is applied and there is a charge, the charge will experience a force, right? This charge will experience a force. But if this charge is allowed to move and it is given a path, it will flow. This there will be a dynamic motion now, right? So this charge will no longer remain at rest. This will go in motion and it will constitute a current, right? So this moving charges we see in our day-to-day life as well, right? In lightning also. Lightning is what? That there is a huge charge discharge from the clouds to the earth, right? But lightning we will not talk. It's not about the steady current. It is like a impulse, right? That for a very short amount of time, right? For a very short amount of time, there is a huge charge and then it falls down to zero. I can say this is at lightning. But in normal devices, in normal appliances, you see, you would have experienced electric shocks and all that. So all those are because of steady electric current. So in this chapter, we will talk about steady electric current, right? So before dealing with that, what is current? What is an electric current? So current is nothing but it is flow of charges, right? Current is flow of charges per unit time. So rate of flow of charges is current. So electric current, it is indicated by I, right? So I is what? I is charge by time, right? If I talk about the small charge and small time, it is nothing but dq by dt. Current is change of rate of change of charge with respect to time, right? So the SI unit of current is ampere, from the scientist Ampere who coined this term and invented things. Now, how can we define current here? You see, if time is 1, I becomes equal to charge, right? So I can say that for a unit time, the amount of charge which flows through a conductor is nothing but current, right? For a unit time, the amount of charge which flows through a conductor is current. So we talked about what is current. Current being a scalar quantity, there is no vector concept and things here, right? So where do we see current? Current can only flow when there is a circuit, right? Electric circuit. Circuit is a closed path, right? Closed path means there is an entry and exit to the path, right? There is no discontinuity in the path. So basic necessity, basic components which are needed for this current is, one is we call as source, which is, let's say, battery. This is a source, right? And let's say these are conductors and there is some load here. Ignore what is this. This may be a bulb. Let's say this is a bulb, right? This is a bulb, and this is conductor connected from source to the bulb, right? But basic necessity for a current is source, conductor, and the load, right? What is this source? This source is battery, right? Source is battery. What is battery doing here? What is the purpose of a battery? So for a water current to flow, there should be what? There should be difference in water levels, right? Then only water current will flow if there is no external parameters. So let's say this is a container and this is again a container. If there is a hole and there is a hole, if I connect this, the water will flow from this to bottom. So there is a level difference here. There is a level difference. Similar way, even in current, you need to create a potential difference, right? You need to create a potential difference. Let's say this is point A and point B. You need to create a potential difference between point A and B so that current can flow inside this bulb, right? And if you're not able to create that potential difference, there is no current gonna flow, right? And to create a potential difference between A and B, I'm connecting it to a source and battery. So battery is creating a potential difference between points in the circuit, which is moving this current to flow, right? Which is deriving this current. So what is potential difference? Potential difference or potential, we already know. It is work done in moving a unit positive charge, right? From one point to another is potential, right? So we have already discussed potential is work by charge and the unit is volt. So work done per unit test charge is potential and it is done by the battery. So battery has a higher potential and a lower potential, right? This longer terminal is a higher potential positive terminal and this is a negative terminal, right? And there is a term associated with any source or cell which is called as EMF. EMF. The abbreviation will be electromotive force. Right. There is a word force in this, electromotive force, right? But this is basically not a force. This is potential difference supplied by this battery to derive current in the circuit, right? Since force is what? Force is responsible for motion. But this battery is responsible for motion of the charges, which is current, and hence the term is coined as electromotive force. But EMF is the potential difference across the terminals of the battery, which in turn creates a potential difference across the load and allows the current to flow. Basically, it is generating that current, right? This is EMF, right? Okay. But when we talk about current, anytime you must have encountered, we talk frequently about two terms, which is potential difference or potential. Generally, we will use the term potential, but it is potential difference. And then another term is current, right? So relation between potential difference and current, right? So there is a Ohm's law. What is Ohm's law? Ohm's law states that for any conductor, right? Let's say there is a conductor and then there is a battery. Let's say this the potential difference is V. The current in the conductor is I, right? So for any conductor at constant temperature and pressure, the current flowing through across it is proportional to the potential difference, right? At constant conditions, be it temperature and pressure, the current flowing is directly proportional to the potential difference applied, right? If I reverse it, I can also say that the potential difference is directly proportional to the current, right? Potential difference is directly proportional to the current. So to remove this proportionality, I'll put a equal to and put a constant, which is R, right? And R is the resistance of conductor, right? So this term resistance, right? It defines itself. What is resistance? Resistance is the property, right? It is the property by which any conductor or any body opposes the flow of current, right? This resistance is the property of conductor by which it opposes the flow of charges across it, right? And unit of resistance is ohm, since it is invented by Simon's ohm and it is indicated by omega, right? It is indicated by omega. The unit is ohm, right? So you might have come across the resistors in your electronic circuit, 5 ohm, 10 ohm. So these are all the resistance, right? These are the resistance value of these resistors. Resistors are the devices. Resistance is a property, right? So how do we define resistance? It is the property of a conductor to oppose the flow of current or charge, right? So this is very clear, Nora. Now let's understand what this resistance is actually and what all it depends on. So the topic is parameters affecting resistance. Okay. First is length. So you can easily say, if my, let's say your path is long, right? Or if your path is very big, or you have a long distance to cover, obviously the resistance will be more. You'll get more hurdles in the path. But if path is short, you won't have more hurdles, right? The resistance will be less. Similar here as well. If the length, let's say this is the conductor, right? Let's say this is conductor, which is connected across a battery. So if length of this conductor is very large, the charges or electrons will have to drift a long distance to constitute the current, right? And if there is a long set of path to be covered, there'll be more restriction. At every point there will be collisions between two electrons, there will be collisions between the walls of the conductor and electron. There will be a lot of parameters inside, internal parameters, but the resistance will be high, right? So I can say that resistance, which is R, is proportional to L, which is length of conductor, right? Which is length of conductor. Second term, second term affecting resistance is area of cross section. So let's say this is a wire, right? This is a wire which is cylindrical shape, right? This is called the cross section. This is a cross section which is circular for this. There can be, it can be even square or rectangle, anything it can be. So you can easily say, let's forget that this is a wire. Let's forget this is, let's say that this is a pipe and water is flowing. So you know, if this area is less, the water flowing will get more resistance, right? But if area is more, water has enough space to flow. There is no tightness. There is no tightly packed parameters here, and hence resistance will be less. Same for current. If we have thin wires and if we have thick wires, right? Thin wires will offer more resistance when compared to thick wires. You can easily say that since the cross section is more, the electrons has, even the particle which is constituting the current has more space now, right? Between two particles the spacing has comparatively reduced, right? So the chances of collision and things gets reduced, and hence it has less resistance. So more the cross section, lesser the resistance, right? So I can also say that resistance is inversely proportional to area, right? Third parameter is temperature. Now, with respect to temperature, how resistance varies. Okay, let's understand what happens if I increase temperature or heat any body. What happens? The randomness increases, right? The randomness increases. The particles start colliding more, right? And hence, you can say that the resistance increases, right? Because the collision will increase, the vibrations will increase. So the dynamic flow will obviously get more oppressed now, and hence resistance will increase. This is the case of conductors. So for conductor, if I increase the temperature, my resistance will increase, right? But same case is not for the semiconductors. We will discuss more on semiconductors chapter, but let's understand that in semiconductor, if you increase the temperature, the resistance decreases, right? In semiconductor, if you increase the resistance, sorry, temperature, the resistance decreases, right? But for conductor, resistance increase with respect to temperature, right? So if let's say if T2 is, there are two temperature, right? Let's say at temperature T1, let's say resistance is R1, and at temperature T2, let's say resistance is R2, right? So you can easily calculate resistance. So this is how we calculate resistance of any conductor with respect to temperature. Alpha is the temperature coefficient of any conductor, right? Temperature coefficient. So this is a material property. Now you see this alpha is positive for conductor, right? But this alpha becomes negative for semiconductors. Now you can say that as temperature increases, the resistance of semiconductor decreases, but for conductor it increases. So this is a relation between resistance and temperature for any body, right? Okay. Now let's forget other parameters for now. Let's understand the physical parameters. Resistance is proportional to the length, and resistance is inversely proportional to the area of cross section. If I take these two, let's say this is equation 1 and equation 2, the resistance becomes proportional to length by area. And if I take the proportionality out and take equal to, this becomes rho L by A. And this rho is resistivity of conductor. And the unit of rho is ohm meter. Right, ohm meter. Now what is resistivity? So resistivity is resistance when length and area are 1. Right. You see the expression rho equal to L, R equal to rho L by A. If L is 1 and A is 1, R becomes equal to rho. So rho becomes equal to R. Rho equals R. Right. So if length of any conductor is 1 meter, area of cross section is 1 meter square, then the resistance offered by that conductor is resistivity. So in resistivity, we have specified the dimensions of conductor. So let's say if there is a conductor, the conductor may be, let's say, square shaped conductor maybe. Okay, this is a conductor maybe. So if length is 1 meter, and let's say this is also 1 meter and 1 meter, which means area becomes side into side 1 square. So resistance offered by this conductor will be equal to resistivity, right? Now, so we understood the parameters which are affecting the resistance, right? Length, area, temperature, and fourth will be what? Nature of material, right? Nature of material, you can easily say that conductor is more capable of supplying more current because it has free electrons, but insulator is not. So this is what nature of material is all about. Even in conductors, you can segregate which one has good conductor, bad conductor, and all that, right? Okay. Now, one more topic will be factor affecting resistivity. Factors affecting resistivity. So we talked that R is equal to rho L by A, and rho is the resistivity of the conductor, right? But when we defined the resistivity, we already said that resistivity is the resistance offered by a conductor of length 1 meter and area of cross section 1 meter square, right? So resistivity is independent now of all these physical dimensions, right? So factors affecting resistivity, resistivity is no longer dependent on length. Whatever be the length, resistivity is not going to change. Whatever be the area, resistivity is not going to change. So what are the factors which will affect resistivity? One is temperature. Other is nature of material. So only these two factors will influence the resistivity. Length and area will go out of the picture, right? Let's understand by an example. right? Okay, let's say there is a wire of length L, right? Wire has a length L. The resistance of wire is R and resistivity is rho. Now what I did is I have cut this wire into two halves, right? So one half will look like this, L by 2. So I need to find what is the resistance of this half now, right? What is the resistance of one half and also the resistivity. So one thing I can say very clearly without looking at this question is whatever I do to this wire, cut it, make it long, change its cross section, nothing is going to happen to the resistivity. The resistivity will still remain rho. Resistivity is independent of the length and area. What will change is resistance. Now I have cut the wire into two pieces. The length becomes L by 2. Area is A here also and here also. Area has not changed. So length has become half. So I know resistance is proportional to the length. So if length is becoming half, resistance will also become half. But resistivity will not change. Do mind that. Okay. Now, let's say this is a conductor, right? This is a conductor of length L. It is now connected across a battery of potential difference or EMF V, right? So this resistance will be given by what? Rho L by A. Let's say I is the current inside the conductor. So we know Ohm's law is V equal to IR according to Ohm's law, right? If I place R from the top, it becomes I rho L by A, right? Now across these 2 points, let's say A and B across this conductor, the potential difference is V, right? But if I need to find the electric field, right? What is the electric field? Electric field, you know, the relation between electric field and potential difference we discussed is E is nothing but dV by dr or d, which is change in potential by change in distance, which basically means potential between 2 points by the distance between those points. So if I talk about A and B, this becomes V by L. So I can also write V equal to E into L. V equal to E into L. Now if I place V equal to E into L here, this becomes what? This becomes E into L equal to I rho L by A, and this becomes E equal to I by A into rho, right? E becomes I by A into rho. So this parameter I by A, there is a parameter called I by A. This term is called as current density. Current density. Indicated by J, current density is given by current per unit area. Current density is a vector quantity. Current may be a scalar quantity, but current density is a vector quantity. So let's say if this is the conductor and A is the area of cross section, the direction of current density is normal to the area, right? And if I is the current in this conductor, the current density is I by A, the magnitude, but the direction is normal to the area. So current density is the vector quantity. How do we define current density? Current flowing through the unit area is current density, right? And the direction is normal outward to the area, right? So let's place this current density over here and let's write that E equal to sigma into rho, E equal to sigma into rho, right? Now vectorically if I write E is a vector quantity, sigma is also a vector quantity, and rho is my resistivity, right? E equal to sigma into, right? No, not sigma. Let me just change this. This is J. Current density is indicated by J, not sigma. So E equal to J into sigma. Sorry, J into rho. So J is what? J is current density. E is the electric field intensity, and rho is resistivity. And this expression is called as Ohm's law in vector form. Ohm's law in vector form, right? So we discuss E vector equal to rho times J vector, right? I can also write this like J vector equal to 1 by rho into E vector, right? 1 by rho into E vector. Rho is resistivity, right? So reciprocal of resistivity is conductivity, right? So remember, conductivity is a term, conductivity which is sigma. This is 1 by rho, which is 1 by resistivity. Similarly, the reciprocal of resistance is conductance, right? So resistance is the property by which a body opposes the motion, right? Opposes the flow of current. Conductance is a property by which it supports, right? Similarly, the reciprocal of resistivity is conductivity, right? So J becomes equal to sigma in times E vector. So in actual terms, this particular expression, right? This particular expression, which is derived of this, is Ohm's law in vector form, right? Ohm's law in vector form. J equal to sigma times E. So we will discuss more about these terms in coming lectures. We will discuss how do we calculate different parameters. We will discuss more on the nature of species which flow inside wire, the drift, how does it drift, what is the velocity by which it drift, and more about these cells, battery, conductors, everything in this chapter. So till then, thanks.